EC 111 Lecture 6 Set 5, more examples for blocking versus non-blocking assignments. Here, what we want to go into is how blocking versus non-blocking make a difference because of the order. Remember, we said blocking is going to block the next one, so you're not going to execute the next one before the first one is executed. So in that sense, ordering becomes important. But of course, in non-blocking, if you're not blocking other people, the ordering doesn't really important. Let's just see some examples of this. So if we have this statement like stated here, we have a Verilog code which is going to generate registers. And here in this particular case, what happens is that the input D is going to get assigned to Q1, and then Q2 is going to get the value of Q1. But this is blocking, so what will happen is this is going to create two registers in parallel because, this is not... this is not really understanding that these two are connected. This is just going to assign values. But in this case, where you are assigning, to this a proper register value, and then your naming implies that these are kind of concurrent, what will happen is that it will synthesize this to two serially chained registers and a circuit that behaves as a 2-bit shift register. One thing I want to emphasize is that this coding style is not recommended. And we will, and then it's easy to see why, because, we don't want to talk about registers and use blocking assignments with them. So this could generate hazardous situations. So you could also split blocking assignment in separate always blocks. In this case, this is going to assign. It's the same circuit that we had earlier, but the splitting will be generating a 2-bit shift register as every time this positive edge of the clock goes, it's going to generate one of these registers, and then this is going to have a race condition in simulation. So this is, again, as I mentioned earlier, these are not recommended practices. We don't recommend that you use blocking assignment within non-blocking shift register assignment. Here is, I'm just giving you some more examples of this. This is a shift register with non-blocking assignment. As you see, everything is clear. We are trying to have a shift registers where with each clock bit, the value in the first register is going to get transferred to the second, and so on. So this is going to behave, fine. And in fact, because this is a non-blocking assignment, the good thing is you could specify this in any order. You don't have to be in order to do this. But if we were doing this with blocking assignment, this would, the first one would block the next one, and, the next one. And then the synthesis actually gets confused in this case, doesn't really even sometimes realize that, this has to be more than one register. In fact, if you did that, what is going to generate in this order, the same order that we used in the previous slide, what it's going to do is it's going to overwrite the same register with the blocking assignment, and at the end, your output will be here will be similar to the first input in that one register. This could have, kind of unforeseen circumstances, and will not be easy for a designer necessarily to see what will happen. You could do a different order here, where we did assign values in a different order, and then it could generate the right result. But again, because here this notion of ordering is important, so ordering in blocking assignment is important, but that's not something you want to necessarily deal with. So for that reason, the recommendation is don't use blocking assignment here. Just use non-blocking assignment. That's a bad practice. So let's go to another example of a counter. That's an example that arises a lot in digital circuits. There are different ways to design counters. The simple ring counter is just the one that ripples, like a application of a shift register. Basically, ripples the values out. So if you have an n-bit shift register, you could make an n-bit counter, and then there are two types of ring counters. There's a straight ring counter like the one we've seen earlier, and there is the Johnson ring counter, a twisted ring counter, which is a complement of the output of the last shift registers to the input of the shift register. So the overhead is a little more. Instead of just the values in the shift register, we have also the complement of the values. But then this would this is another possibility for designing. But ring counter is only using it's using n registers to make n count. This is not very efficient, as we know that with n registers, you should be able to make 2 to the power n possibilities. And then, so for that reason, there is a binary counter that has been introduced. It has more states, and it has, but remember, there is a design. So design always has trade-offs. If you make the design simpler, your hardware is simpler, then your delay may be more. You may not be as scalable. But if you make the design more complex, you could actually make the design a little bigger, a little more delay. But these are things that are basically in the hand of the designer. Not everything is in the hand of the synthesis software. You could give constraints to the synthesis software to try to optimize some of these, but unless you design the right thing, you design the right structure from the beginning, it may not be always the most efficient design if you don't take into account, and that's where the intelligence of the designer comes in. So here, for the rest of the slides, I just encourage you to take a look into some of this, counter designs and using blocking versus non-blocking, and see the applications of that and how that impacts the hardware design. I think, I'm not going to go through each and every detail in the lecture, but I encourage you to go through the details and ask questions if you have any.